Hey everybody, Josh from SILCA here with another hopefully fun video. This one's going to be a little bit out there. It involves a mop head, a kitchen knife, some razor blades, the Microscope, which you guys seem to love. I know I certainly love playing around with it. Today's video, it's about tubeless and sealant and tires. As you all know, we launched Ultimate Sealant 2.0 just a few weeks back. Josh from SILCA here with an exciting new product announcement. Maybe not 100% of a new product, but is a new version of a product, and that is the new SILCA Sealant with Fiberfoam 2.0, also known as injectable Fiberfoam. And huge thanks to everybody. I mean, massive launch. I think we ended up selling out in Europe and in Australia in 2 or 3 weeks. It was a record sellout time. We're almost sold out in America. We are producing it as fast as we can to try to keep up with the demand. And of course, as is, I would say, typical with things that we do, it's an awesome product, but it turns out it's really hard to make, as pretty similar to how Ultimate Sealant 1.0 was hard to make. And so we're making it as quick as we can to refill the stockpile. So if you're looking for it, please give us a little bit of patience and time. We keep selling out. One of the things that I'm most excited about with this product is we seem to be pulling a lot of new people into tubeless and into sealant. And with that, our inbox is full of questions. And we've actually had a couple of really interesting, great questions this week from people who are new to tubeless and new to sealant. And one that I got involved with that really stuck with me was, customer, first-time tubeless user, first-time sealant user, 3-4 rides in, got a cut in his tire and the sealant didn't seal. And, he wrote us and said, hey, I love your products, but this one really let me down. I'm really disappointed. You said it seals 6mm punctures, and it didn't seal this puncture that I have. And, really great customer, enjoyed talking with him, and it got me thinking, we really don't talk enough about the differences between, what is a puncture, what is a slice? One of the things the industry does is has some standards around testing that we all try to adhere to, but one of the problems with those industry standard tests is that a lot of times they're done for the simplicity or the repeatability of the testing, and they're maybe not super clear, what it means to you, what is 150 degree newtons per millimeter of torsional stiffness mean in a frame. Well, the industry knows what that means. It's pretty hard to say otherwise. The industry standard for a puncture, and this is important, is a puncture with something like this. This is my Japanese precision awl, and it is a very sharp precision tool. It is tapered, and you can plunge this at different depths into the tire and say this is a 2mm, a 3mm. We even have a set of tools in our test lab that are specifically fixed at 2, at 3, at 4, at 5, at 6, at 7, at 8. We even have some 0.5mm differences in there. This creates what we call a puncture, okay? So essentially it would be the equivalent of like a thorn going in the tire, a nail, a screw, a staple, right? One of those steel wires from the carcass of a tire that you run over and punctures the tire and you pull it out. This is what the industry standard testing is using. And so when we say 6+ millimeters, it is done with something like this. Now, the thing that's not clear in the way this testing is done, a puncture and a slice are very different, right? A slice is made with something like this, right? A razor blade. And the problem with trying to come up with an industry standard for a slice is that a 2, 3, 4mm slice can be very, very different depending on the tire and depending on the tire construction and depending on the angle of the slice itself. So I wanted to get into with you what's a puncture, what's a slice, and really let's talk about how tires are made, because this is going to be super, super critical to this discussion. Okay, so this is where my mop head comes in. So before I made this video, I stopped at the Kroger and I bought, this is a Liebman mop head. When we look at the casing of a tire, it looks something like this. And in fact, I've got my Microscope here, and let's flip up. Here's just an image of a tubeless tire casing that we will take with our Microscope. And you can see what that looks like. It looks like a bunch of parallel fibers, and every centimeter or so they've been stitched. And so what's going on there is that your tire typically has 2 plies of casing, okay, that we can see in here. And those plies are parallel fibers, and they typically run on a bias at plus 45 and minus 45. So if you were to, really like slice it apart, you would see you've got the ones on the outside run this way, the ones on the inside run this way. 2 plies crisscrossed, okay? And so it's a lot like this. These aren't crisscrossed, but they are parallel. And the thing that's important to remember about that is, so when they make the tire, they put it in, there's a little bit of tension in the mold, and then they are smushing or injecting, or there's a couple different ways of doing the compression molding, the technology, but filling this in with rubber. And we'll look at a cross-section of a tire here in a second. So the important thing to think about is the big difference between a puncture and a cut, right? I can puncture this without cutting any fibers. And even if it's on the bias, if I'm puncturing with something like this awl or a thorn or a nail, right, I can puncture it in a ton of ways without damaging or breaking these fibers, okay? If I'm gonna cut the tire, that's gonna be something quite different. And so, if we kind of look at it for scale, your typical high quality tire is somewhere between 27 and 130 TPI, that is threads per inch. Typically higher quality tires have more threads per inch. The lower quality tires have less threads per inch. You essentially have, just under 1 thread per millimeter. And so a simple way to think of that is, if this is 1 thread per millimeter and I get a couple millimeter cut, right, 3 millimeter cut, I am cutting 3 to 4 adjacent fibers. Now, the way the tire casing works, right, when the tire is inflated, it's a pressure vessel, right? So it's the air pressure's pushing outward, and the casing fibers are handling that by being in tension, right? So the more pressure, the more tension. And this is one of the reasons that tire pressure is so critical in reducing, I want to say preventing, but really reducing the likelihood of flats. And this is where our kitchen knife comes in. So I've brought a nice global chef's knife. And let's think about this, right? So when there is low pressure in the tire, there is relatively low tension in the casing. And you think about, at the micro level, right? If I want to cut this, right? Like you're not going to cut it when there's no tension in it at all. I mean, I don't care how sharp this knife is. Maybe some a YouTube samurai thing, you could cut it. But even I bet then they would slice down on it because you would catch it and you would pull some tension in it that you could then slice across. This is going to be very hard to cut with no tension. So think about if you had to cut this, what would you do? You would grab it and you would put as much tension as possible in it and try to cut it that way. And we see, like, if I pick any one of these and I pull a lot of tension in it, I can cut it quite simply, right? If I have little tension in it, even if I pick a single one, like it's hard to cut. That is essentially why lower pressure is going to lead to fewer flats. And I think, we're seeing that in gravel racing right now, that as we go to more mountain bike width tires and we run them at ever lower pressures, the flats actually come down. And that's because we historically have been kind of over pressurizing our 40 millimeter tires, or call it 40 millimeter tire, for an event like Kansas. You're typically running an air pressure at unbound in a 40 that's really based on not pinch flatting. But that actually has you over pressure for everything else and has you at a high enough pressure that you are more likely to cut that tire. So let's talk about why sealant, how sealant works and why it's different. So you can imagine if, this is your tire casing and you're puncturing it this way. You have a puncture, air will escape. If there were a tube here and no sealant, that's a hole. Air escapes when you remove it. With the sealant, the tire, it doesn't exactly heal, but the casing squishes back together. And really what the sealant is doing is sealing up the rubber that's been damaged with new rubber, right? So sealant is latex. Most tires have some form of natural or synthetic latex in them. And so the sealant is really able to plug the hole in the rubber itself. Something like ours with Fiberfoam, right? You're using the fiber as an occluding agent. So essentially, you're trying to like dam it up. And we've actually got some pictures from the inside of some punctures that we've stabbed. Yep, here we'll show those. Punctures from the inside, shown from the inside, where the fibers have really like flowed up to the puncture, and they filled it. And so 6, even 7 millimeter puncture damage, as long as only 1 or 2 or no casing fibers are cut, you're going to seal every time with something like this. But here's where it starts to get hard. As we cut fibers, the hole remains, and the need to replace the structure of those fibers remains, right? And so in the example of my customer here, he had a 4 to 5 millimeter cut perpendicular to the direction of travel in the tire. And you could even see sort of a bulge locally in the tire where there's just not enough casing structure left to hold anything in. And, you know, even with carbon fiber in the sealant, you know, you're sort of building like a beaver's dam behind that. If, you know, if there's no structure in the casing to support the dam, then with enough pressure, that's also going to blow out. So the other thing to think of there is, you know, you cut, it doesn't take more than a couple of fibers really to cut before the tire really isn't even safe to ride anymore, or it's not safe to ride without some sort of structural boot glued into the backside. So that's the other one that we need to be careful of, right? You got a 4 or 5 millimeter slice in your tire that will not seal with sealant. You probably need to check the structure of that tire. So we've run our mop. Let's look at our 2 types of tires. So these are tires, we talked about them in a previous video, and I had a ton of people asking. We talked about the difference. This is a tubeless tire. This is a tubeless ready tire. So TL, TLR. I got a lot of questions last time. Who makes true full tubeless tires? Honestly, I can't find any right now. True tubeless tires are heavier and have higher rolling resistance, and they're more expensive to make because they have quite a bit more rubber in them. We had quite a few of these 10 years ago. Hutchinson, number of brands making true tubeless. A true tubeless tire is kind of like an automotive, like a car tire. It doesn't need sealant to seal. A tubeless ready tire, which is what really all the tires in the market are today, this is not an airtight tire. This tire needs sealant to fully seal. As I like to say, the tire manufacturers are letting you and your sealant do the final manufacturing step in getting this to be a true tubeless tire. So let's look up close at this bias ply thing and the casing fibers that we're talking about. Okay, so you can really see here the casing plies as we are discussing them, right? So this would be the inner bias ply. What you're seeing here is the inner, you know, call it a plus 45, and then here in the outer you're seeing what we would call the minus 45. Okay, those are your casings. This particular tire is a 27 TPI tire, and so you were looking really at about one casing thread being just under a millimeter, right? There's 27 for every 25.4 millimeters of width is what you're looking at. Let's look at the bias ply in the casing of the tire sidewall. Okay, here we go. We'll get it under our microscope. Let me flatten it. Let me get the... Okay, so we see here, you can see the cords. If you look at it from the other side, you can see the cords run 90 degrees, more or less, to that. And then you can see every so often, like here, where they've kind of stitched that together. Let's kind of take a look. So you see these are the main cords here, and then these are, every so often, they have kind of stitched them together. That helps them stay parallel and flat when they're being molded in the molding process. And then you can see down here in the bead, you actually have a woven fiber. So this would be what we'd call a plain weave, pretty similar to plain woven carbon fiber. And then that's been run around the bead. And then the whole thing is compression molded with rubber. Let's talk about our types of cuts and punctures. So let's look at our awl here. You can see if I take this, I can run this through. I mean, you can just see right there how the fibers get out of the way, right? I can puncture this tire right in front of our eyes, and you can see the fibers are just running around that. And then when I remove the awl, you can see how the puncture, like air is going to escape from that, but you can see right there that there are no fibers cut. Maybe, you know, maybe there's a little bit of damage, but nothing too big. That is going to seal pretty much every time, okay? And because of the consistency of this type of tool, this is the industry standard test. Now, we talked about inconsistency for slicing. Why is it inconsistent? Well, let's look at it this way. So that's our puncture. Now let's think about this. If I were to come and let's think about what's going to happen here. What if I cut the tire and it just happens that I am cutting the tire, get this out of the way, parallel, like right along the casing, okay? So let's look at this. We have now cut this. Let me change my focus. I have no outer ply cut, but 100% of the inner ply is cut. Look at that. As I fold that, you can see the inner ply. That is a cut that is structurally a problem. Let's look at it from the inside. 100% cut perpendicular to the fiber. We have removed 50% of the structure from that cut. Now this may seal because you still have some structure. Let me try to find it again here. You still have some structure from the outer, okay? So this is one scenario, but of course, you know, what are the odds that you cut exactly between the fibers like we just did? What typically happens, what happened with this customer that I worked with this week, is that you are going to cut more or less perpendicular to the travel, right? You're rolling over something that's sharp and it's relatively perpendicular to you. And what happens when we do that? Let's find a new, let's turn the casing. What happens when I do that? Let me get my blade in here. If I put even a couple millimeter cut in that way, it doesn't look like much, and then let's bend it. Let's put some load in it. And what you see is that we have cut 100% of the fibers in the casing at that point. So there's literally, over that 4 or 5 millimeter gap, there is no tire structure left. Sealant may seal that at very low pressures, but it's going to be really hard at high pressures, and it's going to be really hard as the tire rolls, because as the tire rolls, it's being compressed as it goes to the bottom, right? Creates the contact patch. It's being compressed, and you see when I want to display this cut, what do? I compress the sidewall. And it opens right up. And so even if it seals, you know, you stop the bike, you spin it around, the sealant gets in that area, the carbon fibers occlude it. Now when you put load on it every time, it's just wanting to open back up again. That is I would say, almost impossible thing to seal, and that is why we're going to carry a plug. Now, I don't make a plug. There's a bunch of brands out there that do. They all work about the same in my experience, but that needs a plug. And then the real question when you get home is, can I save it with a boot, or is the tire gone? And what's going to happen, again, we're back to our mop here, if you cut enough fibers to cost you a ton of structure, as the tire rolls, that's going to open and close every time. All the load that would be in those fibers are now being handled by the fibers just adjacent to the cut. And so those fibers are now extremely overloaded because, you know, you have one fiber either side that's handling, say, the load of 4, 5, 6, 8, 10 fibers that were cut. Those fibers are now going to fatigue and fail much, much faster than they would have failed otherwise, and particularly at higher pressures, they're now handling extreme loads just to handle the pressure in the tire, and that's before you even get to the tire rolling and touching the ground. So really that's what's going on. Puncture, one thing, very few fibers cut. A cut, man, if you're lucky, maybe you get adjacent fibers, inner or outer, that are still intact, parallel to the cut. If you're cutting cutting across those and you're losing all of them, you're probably out of luck. Carry a plug for that reason. Last thing we'll do with the video that I think is pretty cool, I've got some cross sections here before I throw them down of our two tires, and you can really kind of see this. It's a subtle difference. So you can see here's the bead, these are the Kevlar fibers in the bead here, and these tires are really very similar, except that you'll kind of notice the black wall tire is a good bit thicker on this inner bit of casing. And when I look at that, I actually was trying to measure it earlier. It's about 0.35 millimeters of additional rubber on that interface. And that's why when we look at the tire, you cannot see, you know, when I take this and I show it to you that way, you cannot see any casing fibers visible in it at all. It's got an extra point. And, you know, if this were a tan wall, it would probably just be a little bit darker tan wall than this, because the tan wall is fairly clear, or tan colored rubber in there. You can really see how these fibers are kind of almost right at the surface, like you could feel like you could almost like pick them out with the awl. And here there's no fibers visible, about 0.35 millimeters. What that means in the final tire, when you weigh it, this tire was somewhere on the order of about 85, 90 grams heavier than that tire, and that's all just, it's got that additional coating of rubber on the inside. So it's a subtle thing, but there you go. You can see it. Let's look up here through the middle of the tread. Can you see? Oh, look, they have actually added a ply through here. It looks like 1, 2, 3. Sorry, these are slightly different thicknesses, and our focal plane is really thin. 1, 2, no, actually 4. So you've got 2 plies in the sidewall. You actually have 4 ply, casing plies up here under the tread, plus the tread thickness. I don't see a specific puncture belt. Different companies do it differently, right? Some companies put a different type of fabric up there. Some might put like a plain woven Kevlar. Some might put almost like a thin plastic film in there to help reduce cuts. So you hear different words, breaker strip, things like that being thrown around. But essentially for our purposes, the end result is the same. You have a puncture, you have damage to the rubber, sealant is going to seal that vast majority of the time. I mean, I like to talk about sealant as really being almost like counting cards, right? You can count cards in a game like poker, and that will dramatically improve your chances of winning, right? But it's never 100%. I don't watch poker on TV, but my son's a good player, and you'll see sometimes the person has a 95% chance of winning, and then they flip that next card and they lose because they had a 5% chance of losing, and they just got a bad card. Sometimes with the punctures, that's really what's happening here. We're 95% likely to seal that, but you get a cut, and it's at just the right angle, and you sever just enough fibers that it's not going to seal. And so again, carry a plug. There we go. I hope you enjoyed it. The mop, the kitchen knife, the microscope. It was kind of a fun one to do. I hope you enjoyed it. Any questions, comments, thoughts, leave them below, and we will try to address them in the next video. Thanks as always for watching.